to view our own solar system. I'm Eddie Sweeterman from UC Riverside. I'm joined by my co-conveners, Dr. Victoria Meadows from University of Washington and Dr. Stephanie Olson from Purdue University. Just some quick instructions for our speakers. What we're going to do is have 15-minute talks. I'm going to be sitting right here. At 10 minutes, I'll give you a 2-minute warning, and then we want 3 minutes for questions and changeover. And if you have questions, please approach the mics in these areas over here, please. And so I'm happy to introduce our first speaker, Carlos Ortiz Quintana, who's going to talk about the mean global surface temperature of an Earth-like planet derived from Earth's. Apology. Thank you.
Okay, so hi everyone. I'm Carlos Ortiz Quintana, and I come from the Planetary Habitability Lab located at the University of Puerto Rico at Arecibo. And I'm Professor Abel Mendez's mentor, who is the principal investigator at that lab. My project is focused on the surface temperatures of Earth-like planets, and specifically we are trying to derive a model from the geological history of our own planet. So starting with the model itself, this equation corresponds to a surface temperature equation, which basically gives you the temperatures based on parameters such as the Bond albedo, the normalized greenhouse effect, the stellar luminosity, and the semi-major axis. So this is a result that was published in 2017, and so this has been around for some time already. But what we're saying with this project is that this equation can be summarized in this expression over here. So kappa corresponds to a new quantity that we are defining as the thermality. And so it is kind of like a convenient way of summarizing the effects of the Bond albedo and the normalized greenhouse in the surface temperatures. And that expression also includes the equilibrium temperature at 0 albedo. From the parameters that we have here, one of the most important ones that we want to study is the Bond albedo. And so what we're proposing is this equation of the Bond albedo, which we are assuming a linear relation between the land to ocean fractions of the planet. So essentially, it is a sum of the individual contributions of each surface multiplied by their respective net albedos. In this slide, we also have a table that summarizes some of these parameters for the current Earth. So here what we have is the Bond albedo and the surface temperature. And so these are values for the overall global parameters, but we also have the individual contributions from land and oceans. And based on all of this information, we can compute the normalized greenhouse effect, which is given by 0.382, and the thermal parameter, which is the 1.034 that you see there. Therefore, we want to study 3 main important parameters that are related to the surface temperatures of the planet: the Bond albedo, the normalized greenhouse effect, and the thermality, which again is a new quantity that we're trying to introduce. These equations are the way that you calculate the greenhouse and the thermality, and so they are given by the equilibrium temperature, the surface temperature, and the stellar flux. These are parameters that you can find or get from GCMs, for example. So the idea behind using these equations is to input the results from GCMs into these parameters over here, and so study the relationship that they have with the GCMs. This table over here summarizes some of these values for the solar system. So we have Venus, Earth, Mars, and Titan. And it turns out that for something that we found is that the thermality for Earth, Mars, and Titan can be approximated to 1. And so that's something interesting. For now, as of today, we don't have an exact explanation for that, but that's one of the things that we want to improve and study further. But compare that thermality to the thermality that we found for Venus, which is 2.213. So it is a great change, and that could be explained possibly by the higher temperatures of Venus, or even the higher greenhouse and higher albedos. So for our focus, we are using the idea of the project is to use the different periods of Earth as different exoplanets with similar properties as the current period that we are. So for example, here, basically the Earth of 300, 400 million years ago was a complete different world than the one that we have today. So by using the differences in these parameters, we can then study different conditions of exoplanets. So based on this idea and the changes in the fractions of land to ocean ratios, we then computed this equation over here, which is the model that we proposed for the bone albedo. So this tell us that the net albedo of the land is 0.419, while for the oceans it's 0.211. By applying that model to the surface temperature model that we had already, and assuming a constant greenhouse of 0.4, we were able to compute this blue curve that you observe in the plot over there. Again, this was computed by assuming a constant greenhouse, and this helped us find or study the individual contribution of the changes of land to ocean fractions. And that those contributions were about 2 degrees Celsius of change in the current mean global temperatures. In this plot, we also compare the evolution or changes in the temperatures for 2 different proxies. For example, Royer and Scottes. And so it is important to note there that you observe differences, a lot of great differences between our curve and the changes in the proxies. So we are attributing the remaining effect of the changes in temperatures to the greenhouse. Applying our model to those proxies, we were able to correct for those greenhouse and obtain the evolution of the greenhouse, for example, during the Phanerozoic, which, by the way, those proxies are defined for the Phanerozoic, which is roughly 550 million years ago. And these curves tell us a range for the greenhouse between the Phanerozoic. And so the range can be between 0.37 to 0.47. This is the normalized greenhouse. And so this is one of the important results of our project, because again, by assuming or studying the different periods of Earth as exoplanets, then that range can be used to study possible greenhouse ranges to sustain surface temperatures of Earth-like planets. And this model also predicts greenhouse values above the current value of 0.4 for most of the Phanerozoic. We did the same thing for the thermality. And so we found a range between 1.035 and 1.080 for the thermality during the entire Phanerozoic. And again, this can be used for to study exoplanets, to sustain temperatures similar to what we have here on Earth. So an example of an application that we can do with this model is the TRAPPIST-1 system. So that equation that you observe here is the kappa, or the thermality value that we obtain by modeling these planets for thin to thick, dry carbon dioxide atmosphere. So basically atmospheres made of carbon dioxide with less than 10 bars. And so the thermality for these systems was or is 1.107 according to our model. And so these temperatures that you observe in here are the ones that we computed for using our model. So based on our model, what we can say is that, for example, for planets B, C, G, and H, they are less likely to sustain temperatures similar to what we have on Earth, meaning 0 to 50 degrees Celsius. But for in the case of planets D, E, and even F, they are more likely to sustain those temperatures. So in conclusion, our project was able to define a range of the greenhouse for Earth-like planets with similar stellar flux and similar atmospheres, and that range is 0.3 to 0.5, and that is to support temperate temperatures between the 0 degrees Celsius to 50 degrees Celsius. And that's very important because those are the limits of life that we know so far. Our work also provides a simple empirical model calibrated with terrestrial pilot temperatures to quantify the combined dependency of land-to-ocean fraction and greenhouse temperature of Earth-like planets. And so those two equations that you see there, it's one of the main takeaway points of this talk. This is the surface temperature model, and the other one is the Bonn-Albedo equation. And so our model can be used to test or validate results from GCMs, or even constrain exoplanet surface temperatures from observations. So for additional work, we want to derive a more complete model for the albedo that could include all of the different surfaces for compensating for different surface properties. So for example, ice, vegetation, and even deserts. And that's important because different exoplanets will have different types of surfaces. We also want to compare our model with results from GCMs, for example, Rocket 3D. We want to apply our model to the potential exoplanet surfaces, such as TRAPPIST-1 that I already presented some of the results that we have so far, but we want to improve that and test different conditions for those planets. And we also want to use this work to try and characterize a circumstellar temperature zone, which, in other words, it's just trying to study a zone for planets that have temperatures from 0 degrees Celsius to 50 degrees Celsius. And I would like to thank my advisor, Abel Mendez, and the NASA Puerto Rico space grants, which were the ones that funded me for this project. So that will be all, and thanks for your attention.
Those with questions, please raise your hand or approach the microphone. Introduce yourself and your affiliation.
Yes, Eleonora Ley from ETH. Maybe a naive question. I don't know. Can you go back to the previous slide? Great. Yeah, so say that we detect, well, we have an estimate of the surface temperature with future missions, talking about 20 years from now. Could you, at that point, get an estimate of the fraction of land versus the fraction of water, or is it totally unfeasible?
I think that potentially we could, because if you know the normalized greenhouse effect, for example, you will essentially, and if you estimate the surface temperature, you will eventually find the Bonn albedo, and so by finding the Bonn albedo, you could get a known at least diffraction between land to ocean of the planet. So yes.
Awesome, thank you.
Are there any other questions? If not, I've got one quick question, which is, how do you account for clouds?
So in this model, we still haven't considered the clouds. Well, those net albedos possibly have some contribution of clouds, at least in the land albedo. But directly, we are not considering that. That's one of the possibilities to consider for the entire model.
All right. So, oh, where? Is it on the? No, I didn't see it. A phone. Okay. Our next presenter will be Tim Livengood, and let's hope your notes here. Okay. Who will be now talking to us about a comparison of the Earth's poles and signs of habitability. Although I can see it here. Can we see it on the screens here? Yes? Okay, we can't see it here on the presenter's podium.
I'll try to leave and come back.
Well, you can see it. Oh, there we go. Here we are. We're finally loaded. Okay. All right. Away you go.
All righty. Keep your distance. I'm becoming a plague rat here. All right. Good afternoon. I spoke this morning presenting Roderick de Kock's work on looking at the, there it is, of the phase variation of visible light signal from the Earth. Now I'm going to give more of a general overview of the polar observations that were a part of that work. What you're looking at there are the time average north and south polar images that we built up from 24-hour observations of each of them. North is on the left, south is on the right. All right. This results from the epoxy extended mission of the Deep Impact spacecraft. Epoxy is a pun on extrasolar planet observation and characterization mixed with the Deep Impact extended investigation after NASA headquarters told us that we could do both, but we had to do it on the budget of one of them. And then they cut that budget. But anyway, so we made the Earth observations. We had 5 planned observations in 2008. In March through June, observations number 2 and 3 were canceled, which leads to the weird nomenclature that you'll see. And then we followed up in 2009 with makeup observations for those 2 lost ones from 2008 that happened because of the orbit the spacecraft was following to eventually get to Comet Hartley 2 to be able to observe the Earth at very high latitude. So we were able to do each of the north and south, and for no special reason, they ended up in both cases being at the respective vernal equinox. But that does affect any conclusions might be related to seasonality of the Earth that you might be observing there. The instruments we used, there's a visible camera with 7 different filters, 100 nanometer bandwidth each nominally, with some limits at either end due to the restrictions of CCD technology, and spaced every 100 nanometers on the 50s, and a near-infrared spectrometer operating from just over 1 micron to a little under 5 micron. All right, we have previously published the equatorial. I don't think that's me making, okay. So we previously published the equatorial observations a long time ago, back in 2011, showing the 3 that were conducted then, and you can see we were in astrobiology. We got the cover, man. Showing, among other things, we had this very nifty observation with the moon actually transiting the Earth during our observations so that we could see the effect of an exomoon on the light curve of the individual planet. That's not something you would normally expect to be able to capture for an exoplanet because if you have to assemble your data over months, you're not going to be able to get, to organize those individual events. But it was good to know how much of an effect it had. Spectroscopically, the moon and the Earth are very different due to the fact that one of them has an atmosphere. Although, surprisingly, at the time that I collected the data, I didn't understand it because it's not doing, spectra of rocks in space is not my thing, but you can now clearly see the 2.8 micron hydration absorption in the moon, which was identified after we had gotten this. It's like, dang, I didn't know. You can also see we fit the long wavelength end to get an effective color temperature for both the Earth and the Moon. That was actually in reasonable approximation for the emergent spectrum of each planet. The polar observations came out a little bit differently. I had to change the scale of the figure, otherwise they would have completely covered the entire thing. The relative scale of the images is correct. We were much closer when we observed the poles than we were when we observed the equator. Just so you'll know, the color map that we chose for this, the red image in the color images is actually the differential index between the near-infrared and red filters, which is why southern Africa is so nice and bright and red there to show you where all the plant life is. The spectra of the polar regions and I used the first of our Earth observations to compare here, are noticeably different, but primarily due to just the difference in the total illuminated surface of the Earth. We did, however, get a different color temperature. The brightness temperature of the polar observations is significantly less than the brightness temperature of the equatorial observation, but the color temperature is noticeably greater than the color temperature of the other observations. And we have to examine that a little bit to make sure that there's really meaningful physics in that, as opposed to I just chose the wrong interval on which to fit. I've also compared a bunch of reflection spectra from the USGS library to show how they do or fail to relate to the spectral features that are in the observed spectra. So for instance, you can see the big water absorption bands in lawn grass, which doesn't cover the whole world, but it does cover my backyard. To show a little more on how the spectrophotometry of the images works out, in each of these I've got a simulated visible light image constructed from the different filters that we employed. And on the right-hand side is that differential vegetation index measurement combined with green and blue to show you where all the plant life is. And if you look down at the bottom edge for the 24-hour average in each case, you can see some of the important contributors to what you would observe if you were an alien observing from our North Polar region versus observing from our South Pole versus observing from our equator. So you can see on the left-hand side, which shows the equatorial observations, that the fact that the northern hemisphere is substantially redder than the southern hemisphere in this color map is indicating the existence of much more continental landmass with plant life on it that appears in those images. And so when you see that in the middle set, which is looking at the North Polar region, you can clearly see that nice pink polar cap region. And that's due to the fact that Asia and North America just completely dominate the landmass that's available to see. Whereas in the South Polar one, the tip of South America, the tip of Africa, and a little bit of Australia can be seen in the individual frames. There's 96 frames. If you want, you can come to me later on. I can show you the movies. They are cool to look at. But it's much bluer in those South Polar ones because there's very little landmass contributing to what is possible to see. And so if you were, for instance, looking for something like the vegetation red edge, the Earth you would see from the South Pole would be significantly different from the Earth you would see from the North Pole. And you might draw different conclusions as to how much plant life there would be on Earth if you were using just that property. Along with the fact that, as it happens, the spectral slope of lunar regolith is so steep that the standard differential vegetation index makes the moon look green and verdant by comparison to the Earth. So it's a limited tool. A little bit more just showing the near-infrared spectra, or actually I've combined the spectrophotometry with the reflected near-infrared spectrum on the left, and then we have the thermal emission is over on the right, also indicating a number of different molecular species that contribute to what we see. Of course, there's a lot more molecular species than that in the Earth's atmosphere, but the ones that make a measurement that you can plainly see with your eyeball are the ones that I've indicated here. Let's see, just a last little bit more about the vegetation red edge there that I've indicated the filters that we would compare to each other in order to make that calculation with the polar observations on the right compared with equatorial Earth 1, and then just the equatorial Earth observations on the left, just to show that, again, it's a potentially misleading measure if you're going to try to use that. The deepest absorption in the Earth's visible spectrum is at that 650 nanometer region, which happens to also be where you have the deepest absorption of the visible ozone band. So there are some real challenges there with trying to get visible light information to describe the Earth. The thing that's really distinctive about the Earth compared to all the rest of the solar system is the strong Rayleigh scattering at short wavelength, where the Earth is really bright. The Earth is the only object in the solar system, it turns out, that is at present very blue and also very red. There are some that are one or the other of those properties, but Earth is the only one that combines them. Last bit, this is something that you may have seen in Roderick de Kock's talk this morning that I showed you, but just a reminder that the polar observations of the Earth have a much higher, a noticeably higher albedo. And if you were to try to model them with a Lambertian phase function, you get a substantially different answer for the geometric albedo fitted to the polar observations than you get fitted to the equatorial observations. The equatorial observations agree with each other. The North and South Pole pretty much agree with each other. But even though in principle, they all belong to the same planet, but you wouldn't necessarily recognize that if this were the only kind of data you have. So next steps, well, it's been 11 years since we published that equatorial observation paper. It is time to get out the companion paper for the North Polar and South Polar data. We've also have not yet gotten around to looking at the rotational modulation of near-infrared spectral features. We have light curves from the rotation of the equatorial observations, and that was in that astrobiology cover I showed you. We haven't done that to look at the near-infrared components yet, and we haven't looked at how the molecular absorption bands in the atmosphere do or do not reflect what's going on with surface phenomena beneath. We haven't looked at the phase angle variation of the near-infrared spectral features, so that's got to come up. And we haven't really tried yet. I mean, there's a lot to do. There's a lot left to do, so we're underway on that. We had Roderick de Kock's paper this morning, and he is working on a paper on modeling our phase behavior for a spherical model. And I'm done. Did I leave any time?
No.
That's me. See, Roderick's talk is much better organized than my own.
There you go. You just hit it. Okay. All right then. So are there any questions for Tim? I'd like to come to the microphones. There we go. You have a question?
Hi, I'm Angie from Purdue University. I was curious about the equatorial view on the big figure you had. Could you talk a little bit about the red limb on the edge of the atmosphere?
Well, some of that is probably just the fact that these are data of limited quality. The camera was intrinsically out of focus. The guys from Ball Aerospace did say, lesson learned, never fly a camera that you can't focus. And so we do have some defects like that. For the most part, we use the direct images of the Earth to convince ourselves that we're not making things up, but that we don't actually use them for science.
Okay, thank you.
Okay, let's thank Tim again. Okay, so our next presentation will be by Rudy Garcia. And he will be talking about demonstrating a diversity of evolutionary scenarios for Venus with generalizations to stagnant lid exoplanets.
Just setting my timer real quick. Cool. Hi, everybody. Yes, I will be demonstrating a diversity of evolutionary scenarios for Venus. I'm going to talk about how we can generalize those evolutionary scenarios to stagnant lid exoplanets. So firstly, when we talk about exoplanets, we want to talk about, whether the ones that we observe are habitable or not, because that's where we can direct a lot of our observation time. Now, to quantify the habitability of exoplanets over time, because habitability is a very dynamic concept, whether a planet is in the habitable zone changes based on how its star evolves. So, of course, to take into account this dynamic concept, we have to think about different geochemical timescales. Specifically, what I think a lot about is the outgassing of water from the interior of a planet into its atmosphere through volcanism. And then I think about the atmospheric escape of that water from the atmosphere into space. And so the balancing of the timescales of those processes typically will tell us how planets can evolve to either a state kind of like Earth, where liquid water is stable, or a state like Venus, where liquid water is unstable. If you're interested in these kinds of timescales, like how the stellar evolution affects all of this, you should check out Evan Davis's talk Thursday at 1:25 p.m. in 301, 305. And if you're interested in the details of atmospheric escape, you can check out Megan Jaluka's talk Thursday, 3:49 p.m., again in 301 to 305. So in order to take into account these geochemical processes, we want to model exoplanets. Now, the issue with that is that exoplanets have relatively unconstrained interior properties that can lead to a wide variety of atmospheres and forward models. There's just not a lot we know about the interiors of these planets. And so this is where the solar system comes in. Instead of looking at exoplanets, we can use Venus as a test bed for models of stagnant lid planet evolution because it's slightly more observationally constrained. So there's not a lot we know about Venus, but we know more about Venus than we do about basically every other exoplanet out there. Now, how do we take these models and how do we simulate the evolution of the interiors and atmospheres of these planets? Well, I do it using vPlanet, which is a code spearheaded by my advisor, Rory Barnes, at the University of Washington. The way that it works is it basically couples all of these different differential equations that model the different geological processes and then evolve the planet over time. So, for example, if we look at the atmosphere layer of the planet, we can see that magma and extrusive volcanism eruptions, they outgas volatiles, especially water, into the atmosphere. And then potentially, depending on the XUV radiation environment in that planet's stratosphere, that water could be photolyzed and escape out into space. Now, the rate of eruptions over time tells us how much water reaches the atmosphere over time, potentially to replenish any that's escaped. And in order to track, my bad, if you're interested in how we can view these atmospheres, you should check out Miles Curry's talk at Tuesday, 1:15 p.m., again in 301, 305. And if you're interested in how we know what we're looking at when we look at these exoplanet atmospheres, you should look at Samantha Gilbert's talk Friday at 1 p.m., again in 301, 305. I guess I'm the only one in Salon West. So in order to track these eruptions over time, we need to model how the planet's mantle changes. You see, the mantle is heated primarily by the decay of radioisotopes and by heat flow from the core. And then the mantle has two distinct ways to cool. One way it cools is through those eruptions. If you erupt all the hot melted rock, you cool off the mantle. And what's key to that is that by erupting that hot melted rock, you're taking volatiles like water or carbon dioxide and putting them from the interior into the atmosphere. The other way that mantles cool is through convection. Convection basically, rotates the mantle and it pushes sort of hot rock upwards and pulls cool rock downwards. Now, convection is limited by this thermal boundary layer in the mantle. At that thermal boundary layer, convection kind of stops being efficient and heat mostly gets out via conduction. And then getting out through conduction continues on in the crust. And so no matter how convective your mantle is, your heat transfer is still going to be limited by that conductive thermal boundary layer, which is determined by sort of how viscous your mantle is. So that thermal boundary layer represents the beginning of the crust and potentially the stagnant lid, which is true because we're going to be talking about Venus. In fact, if we follow those volatiles, the water, the carbon dioxide, and the incompatible elements like the radioisotopes in the magma, that magma will melt, it'll rise, and while some of it does get erupted to the surface and outgasses, many of those volatiles will actually be trapped in the crust. And this is called intrusive volcanism because it's intruding into the crust. Now, on planets like Earth with tectonic plates, any volatiles that are stuck in the crust are relatively easily recycled back into the mantle through subduction related processes. However, on a planet like Venus with a stagnant lid, it's kind of more up in the air whether those volatiles will get recycled back in. However, recent work, such as Brad Foley's work, has shown that even though stagnant lid exoplanets and stagnant lid planets don't have tectonic plates, they can in fact recycle some of those volatiles back into the mantle, mostly through phase changes and density changes that occur on the lower crust. Causes that lower crust region to sink back into the mantle, bringing back those volatiles and kind of completing the cycle. Now, like I said, the mantle is also heated by the core. And the core itself is mostly heated by either secular sort of leftover heat from formation and by the decay of radioisotopes. Now, the core mostly gets that heat out through convection. And if the core convects vigorously enough, then we're going to have a magnetic field on this planet, which is something that we can potentially observe. The other interesting thing about the core convection is it really relies on whatever the temperature of the lower mantle is. That kind of limits whether the core is going to convect very vigorously or if it's not going to convect much at all. And so overall, when we put all of these layers together, we get this kind of whole planet coupling approach. And the reason we do this is because, as you can see, each of these layers kind of acts as a boundary condition for all of the other processes in the planet. Convection in the mantle is limited by the thermal boundary layer, which is itself kind of due to the viscosity of that mantle. And the viscosity of the mantle changes based on the temperature of the mantle and the amount of water in the mantle. But of course, the mantle is getting heated by the core, and whether the core convects vigorously enough for a magnetic field, well, that's limited by the mantle temperature. So you get these really interesting and kind of complicated feedbacks that I'm going to go into in sort of detail, enough detail for this talk. Now, looking at this model, you can see that there's lots of knobs to turn here. This is a really high-dimensional problem, and it requires a thorough exploration of parameter space to find our distinct evolutionary tracks. So what we did is we ran about 24,000 simulations, sampling about 15 different parameters, which if you're interested in the real details, you can talk to me later. But we took those simulations, and then we took the subset of those simulations that matched modern-day Venus. So our constraints for Venus are threefold: the water in its atmosphere, the carbon dioxide in its atmosphere, and the fact that we don't see a magnetic field on Venus. There is actually a little bit of water in Venus's atmosphere. It's at about 30 parts per million. So there's a little bit that we can constrain. So on this next slide, I'm showing the diversity of evolutionary scenarios that lead to modern Venus. Each of these lines represents a single choice of parameters for a single simulation over time. So this top figure represents how much water is in the atmosphere of Venus over time. In the middle, we can see how much carbon dioxide is in the atmosphere over time. And on the bottom, we can see what the magnetic moment of the planet is over time. The different colors represent different groupings, different potential evolutionary scenarios. You see, while different scenarios converge on our defined constraints, they diverge for other values. So on the top layer here, we can see the top row has, again, on the left, the amount of water in the atmosphere, and on the right, the magnetic moment of the planet. But on the bottom, we can look at some of these derived parameters where we can see divergence in these evolutionary scenarios. In the bottom left, we've got the surface heat flow of the planet, and you can see that these blue simulations end up with high heat flows, and these kind of pale white purple simulations end up with very low surface heat flows. And then, of course, we've got the percent of the core that's frozen, and that's in the bottom right. And there are all these red simulations that end up with Venus having a slightly liquid core. And so what we've defined here, what I've done a lot of work doing, is sort of categorizing these potential evolutionary scenarios. We've got in the red these scenarios that end in a liquid core, and in the sort of white-yellow, we've got these low melt fraction scenarios where Venus ends up with a very low melt fraction. If you look closely at the top left plot, you'll see that all of those sort of whitish, yellow, purple simulations, those are all really rapidly decreasing. And so this is actually a very transient scenario. In these simulations, Venus has such a low melt fraction that melting is actually about to stop. And so if I continued these simulations past 4.5 billion years, even to something like 4.7 billion years, Venus would lose its water in its atmosphere because melting would stop and outgassing would stop. Now, what's really cool, and something I've been working towards, is trying to find the differences in these evolutionary scenarios that could be distinguished observationally by future Venus missions. So this is a pretty complicated staircase plot. Each point represents a different simulation in this 5-dimensional parameter space defined by potential observables on Venus. All I really wanted to talk about this plot, though, because I don't have much time, is that you can see that the color-coded groupings are distinguishable for certain observables, especially the surface heat flow of the planet. I don't know much about the future Venus missions, but I came to AbSciCon to find out more because I think there might be some cool stuff we can learn about Venus's past. Lastly, I want to say that the evolutions that result in a Venus with low melt fractions lose a larger amount of water to space. So on this top panel, we can see how much water is lost for each individual point simulation from the mantle. In the bottom 2 panels, we can see where that water goes. You can see that these simulations that end in a low melt fraction, they actually lose much more water to space than basically all the other simulations. That's interesting. We might be able to predict some sort of observational discriminant from, for example, the DDH ratio in Venus's atmosphere. Gonna skip this slide. It's got a lot of details, but I don't have much time. I want to leave time for questions. So my conclusions are that whole planet coupling is needed to both match solar system planets and take into account interactions on exoplanets. Venus could be in the process of water loss from the mantle due to a dearth of magnetism, or it could be in a relatively steady state with a meager amount of water being replenished by outgassing. And lastly, Venus histories that match modern day observations cover a wide range of parameter space that demonstrate both the evolutions that exoplanets could have and the need for analysis techniques that take into account the uncertainty of possibilities. Thanks.
Okay, questions? Ah, Auntie.
Hello, Antigona Segura from the National University of Mexico. There was, could you go back to the plots where these 4 plots where you have the frozen core? Yes, but the other one, the frozen core.
Oh, this one. Sorry.
Is that right? So what I see there is that the core is frozen for those red lines, some of those red lines, and then the frozen part shrinks, right?
Mm-hmm. Yeah.
Where does the heat come? What is going on there?
Yeah, so I think what's probably going on there for the simulations where the core actually starts frozen and sort of starts melting is I think the core is actually heating up, potentially due to changes in the lower mantle. So if you imagine, right, if the lower mantle heats up a lot due to whatever's going on up there, then the temperature difference between the core and the lower mantle is going to go really low. And so the core isn't going to be able to get heat out very quickly, and that's going to result in the core net heating over time, and that melts the core a little bit. So really, it's kind of a whole planet coupling thing. The lower mantle sets the boundary condition for the core, and if whatever weird stuff is going on in the mantle kind of trickles down to really influence the core. Thanks.
All right, Tessa and then Tim.
Hi, Tessa Fisher, ASU. Did your research shed any light on sort of the opposite question of why do certain planets avoid a stagnant lid sort of end state? I know for Earth, I've seen that attributed to everything from having a biosphere to the giant moon-forming impact.
Yeah, I think that's a really good question as to why planets don't enter a stagnant lid, especially if we take stagnant lid as the kind of default. I haven't really looked into that. We kind of, in this work, I just kind of assumed Venus has a stagnant lid the whole time, but it's something I'd love to look more into and incorporate into my models.
Thank you.
Okay, quick question and quick answer.
Hi, Tim Livengood, University of Maryland and Goddard Space Flight Center. I am hungry for something that's at a next level of detail that you didn't get into, which is in the atmospheric loss process. If you can make predictions for the enrichment of heavy isotopes, because that's something that we can measure both remotely and then when Da Vinci gets there and plunges through. and actually get some direct measurements on CO2 and water and so on in the atmosphere. So would it be possible to incorporate that?
Yeah, I would love to. It's something I looked at a while back, but ran into some issues with. But I'd love to talk offline later about how I can incorporate more observable concepts into these kinds of models. Thank you.
Thank you.
Okay, unfortunately, we're going to have to move on. So if you could ask Rudy, he's just going to be sitting right here after the break. That would be great. All right, so we are now moving to a remote presenter, and I'm going to hand over to Stephanie. But thank you again to Rudy.
All right, our next speaker is Johnny Seals of Rice University, and Johnny will be speaking to us about the species richness of exoplanet mountains.
Johnny, can you bring your slides back up? There you go.
Can you see them okay, and can you hear me?
Yes.
Yes. All right, thank you. So today I'll be discussing the species richness of terrestrial vertebrates and rocky exoplanets. I've done this work in conjunction with some collaborators listed at the bottom of the screen that range from geomorphologists to structural geologists to biologists. One of the interesting things that they've taught me is that most terrestrial vertebrates live in the mountains. I think that this is depicted well within this figure from Robeck et al. 2019, where they're showing for mammal, bird, and amphibian species, the proportion of species range in mountain and lowlands. So at the lower greens or at the lighter greens, many of the species are living in the lowlands, whereas at the darker greens and into the black, the species are more inhabiting higher elevations or in the mountains. So they actually found that about 87% of all of these species are living within the mountains. This also reminded me of an interesting problem related to geodynamics, one that's often given within the context of some modeling classes. And that's, can you estimate what the maximum height of a mountain will be based on a planetary size? So one way to go about doing this is to assume that the stress imposed by an overlying column of rock is going to increase as the height of the mountain increases. Once it surpasses a particular threshold, the rock below will crack. So that's going to give us the highest mountain that we could have. Now, if we think of a planet and then compare it to a planet that is less massive, which will have a lower gravity, then due to that reduction in gravity, the maximum height of the mountain will actually increase. We can think about whether or not this bears out in our own solar system, and essentially it does. For Earth, the largest mountain itself is approximately 10 kilometers, whereas on Mars, a smaller planet, the largest mountain is around 24 kilometers. So when we take these two pieces of information together, it suggested to our group that we could ask, how does the species richness of terrestrial vertebrates vary with planetary mass? We'll go about trying to create a theoretical model to answer that using the following equation. We'll first step through the calculating the number of species per unit area and how that varies with height. The way that this was done is that Maya stepped through some data sources and looked at the number of species that were out there and took each species, estimated its average elevation that it occupied, and then binned all of those species into 200-meter elevation bins. Simultaneously, she took the global relief model that is 2x2 cells and took each of the elevations and binned those into 200-meter bins as well. So this allowed for an estimation of the surface area for a particular bin. You can take and divide the number of species by the area of the bin that it inhabits. And she found these results. Here is showing elevation on the horizontal axis, so 0 to 5 kilometers. And then the data resulting of the species per square kilometer on the vertical axis. And this is going for amphibians, birds, and mammals. The same signature is seen within the data, where at as you increase the elevation, the number of species per unit area increases. This continues until approximately 3 kilometers where there's a rollover and the number of species begins to decline. Now, to use this within our theoretical model, we fit this equation to, we chose this equation over regular quadratic to capture some of the asymmetry that we saw within the data. So we'll take our best fit solution, the black solid black line here, and use this within the remainder of the talk. If we combine all of those data and curve, we can import them into our guiding equation. And then next we can think about how is elevation going to be related to the amount of surface area that it composes on a planet. Well, this is where hypsometry comes in. And hypsometry is the science of measuring the elevation and depth features on a planet's surface with respect to sea level. If you're unfamiliar with hypsometry, here's the hypsometric curve of Earth. It's showing the cumulative area on the horizontal axis with 0 on the left and 100% on the right, and elevation on the vertical axis, showing that the deepest points are down around 10 kilometers and the highest between 7 and 8 kilometers. This is showing from moving from left to right, mountains, which do not compose a large cumulative area, into the continental plains, which are making up the vast majority of our exposed continents. And then as you move below sea level, you have continental shelf and slope, followed by the abyssal plains, which compose the majority of the ocean basins, and then moving into the trenches. Each of these features can be related to underlying mantle convection. Here's a cartoon of that mantle convection. Here I'm assuming the operation of plate tectonics, different from what Rudy was just assuming in the operation of a stagnant lid planet. Now to actually show you where this cross-section is located, I have the figures on the left that's showing a representative location off the west coast of South America. And what's occurring in this cartoon is that you have mantle convection that's occurring within the interior of the planet, and its role is to eliminate the heat that's produced due to the decay of radiogenic elements. Now, as the rock is in motion, warmer rock is being brought to the surface, and it's producing melt. This melt is generating new plate, and as that plate moves away from the plate boundary, the spreading center, which is indicated by these red blobs, the plate cools. As it cools, it thickens and becomes less buoyant, and therefore it subsides. It continues to do this until it reaches the boundary, the other plate boundary, which is going to be a subduction zone. Now at this plate boundary, you have the convergence of two plates. The resulting behavior is that you have an increase, you have a production of mountains, which we can model and estimate how high those mountains are. So we can take and incorporate these aspects into a model to help us to estimate what the hypsometry is of a planet. The steps that you go through to calculate this is understanding the mantle thermal history. That's going to feed into a calculation of both plate velocities as well as oceanic crustal thickness. That the velocity and the crustal thickness we're going to relate to mountain height, and then that's going to feed into our calculation of hypsometric curves. So if we go through and show a representative case that we've done for Earth, the modeled value is on the left and the actual value is on the right. The difference in the curvature is that on the left model, I've kept it in terms of how I presented the geological setting. If you were to flip the abyssal plane, so the result from subsidence of the lithosphere from left to right, you would get a similar type of curve that you see on the right. And we are capturing the general trends as well as the general values. So we can take and plug this into our larger model, and then we can ask ourselves, does this model even work for Earth? Well, if we try to calculate the number of terrestrial vertebrate species from our model, we estimate there's 20,500. The actual value is somewhere around 21,000. So we're at least within the ballpark, good enough for the remainder analysis of our work. So what we'd like to do now, having this calibrated for Earth, is extend it to planets larger and smaller than Earth. Now to do this requires that we make some modifications to our mantle thermal history model. So we're going to account for how the mantle thermal evolution occurs over 4.5 billion years until present day. And then we're going to compare the hypsometries for different mass planets at present day. Calculating that thermal history will propagate to the rest of the model and give us those hypsometric curves. Rather than show you individual hypsometries, I'll take a moment to step through what I think are some interesting aspects of those hypsometries. What I'm showing on the left is maximum elevation. What I'm showing on the right is exposed land fraction. In terms of maximum elevation, notice that this line here is representing sea level, whereas on the right is showing the the red line represents the land fraction of Earth. Notice that the maximum elevations on the left are much higher for planets with smaller masses, and they decrease as you increase the planetary mass. And then the surface area, or the exposed land fraction, decreases as you increase the mass of the planet. So how does the number of terrestrial vertebrates vary with planetary mass? Well, if we combine all this together, what we're seeing is that the relative number of vertebrate species is much higher for planets of low mass planets than high mass planets. In fact, there are 3 to 4 times as many terrestrial vertebrate species on smaller planets than larger ones. What I would like to do is offer a caution, though, that there's little in the way of path dependence of life within this model. So we've taken the only planet that we know of life, which is Earth, and extrapolated that to every other planet. Also, there are other planetary cooling regimes, such as stagnant lid, which Rudy just talked about. This itself is going to affect the hypsometry that would be calculated. And then on top of that, we need to think about the water cycling. So how much water we assume is at the surface of the different planets is going to influence the amount of exposed surface area. With that, I'll take any questions. Thank you.
Great, thank you, Johnny. Do we have any questions for our speaker?
Hi, Abel Mendez from PHA Lab UPR Arecibo. Johnny, great talk. And I wonder about what you said about the scales of the mountain. Usually that's because you have more precipitation in those mountains, so you have typically rainforests. But what will be the diversity for as compared to other rainforests that are not that high, or other locations that they're flat relative to
So are you
rainforests?
asking, if I'm understanding you correctly, you're asking why the smaller planets ended up having higher mountains than larger planets, is that correct?
More into the biology, more into that scale applied to mountains, how that scale applying to other forests on land that are not that high.
Yeah, I understand. Okay, so one thing that we didn't take into account is how the diversity, how the species richness is going to vary, of course, in those planes, as we don't have that constrained within this model. This was more looking at the effects of changes in elevation than that. So yes, that would be something that would be important to incorporate in future generations of the model.
Perfect, thank you.
Thank you, Abel.
Are there any other questions? Okay, I actually have one.
Sure.
This is Stephanie Olson from Purdue. And I know you were specifically assuming the presence of plate tectonics, but I'm wondering if you could comment on what your work might imply for a stagnant lid planet and the diversity and complexity of life that might be possible on those worlds.
So that's going to, I think, we don't really have a good idea of the hypsometries of stagnant lid planets. That's going to change things drastically because the size of the mountains that are produced on the plate tectonic planets are going to be due to collisions of plates, which is going to set your actual height. Whereas for stagnant lid planets, you are going to get mountains that are produced, as I showed with Mars, right? That's the largest mountain in the solar system. But those are through different processes, such as volcanism. right? So the dominant driver of elevation and topography is more going to be due to the volcanics than the collision of plates. So you'd have to go through and be able to understand how that's going to change as a function of mantle temperature and planetary size.
Great, thank you.
Yeah, thank
Let's
you.
thank Johnny again. So our next presentation actually was withdrawn. And so we will have 15 bonus minutes before our next speaker. So I thought we could take this opportunity to ask any questions that you might have of our first 4 speakers. I know that there were some questions for Rudy that we didn't have a chance to get to. I don't know if everyone's still here. But, all right, come on up to the microphone.
Hi, Arno Salvador from Northern Arizona University. I was wondering about the Venus evolutionary scenarios. What are the actual initial water content considered in the model, and how this could influence the results and the pathways? Thank you.
Hello. Yeah, that's a good question. So our initial conditions for water are between 2 and 10 terrestrial oceans that Venus formed with. So it's kind of based on some of Sean Raymond's work on like how much water did Earth and Venus start with. And then that's one parameter. And actually another parameter is how is that water, distributed. So that goes between 50% in the mantle all the way up to 90% initially in the mantle. And interestingly enough, the simulations that have a high initial water content, especially in the mantle, those simulations really match Venus. And below a formation of about 4 terrestrial oceans in the mantle, we didn't get any scenarios that actually reproduced modern day Venus.
And then just a follow-up question. What about the time scale then if you have a large amount of water in the mantle, to lose that water and reach the current atmospheric water content on Venus? What's the time scale for that?
Yeah, so that actually happens pretty quickly. It's about like on the order of like tens of millions of years. So it's like a very, very steep drop, and then it gets kind of maintained and outgassing after that like initial, okay, we're gonna lose basically everything in the atmosphere really quickly because atmospheric escape tends to scale, at least in our model, with the amount of water in the atmosphere. After that, it hits this kind of steady state where outgassing and atmospheric escape balance each other, but that's not, it doesn't always have to hit a steady state.
Mm-hmm. Thank you.
Thanks.
Any questions for any of our other speakers?
So we also have a poster session right after this talk at 4:30. Are there any poster presenters here who want to just say a couple words about their posters?
The answer to that question is yes.
I'll volunteer so that Jonathan doesn't feel left out. So hi, I'm Emily LaFleche from Purdue University. I'll be presenting my poster today. It's called Modeling Nitrogen Cycle Seasonality on Early Earth and Earth-like Exoplanets. I guess to give a very, very short synopsis of this, we noticed that oxygen has a pretty significant seasonal cycle. And we also know that oxygen has a very strong impact on biological productivity. And so that will be explained more in detail when you come see my poster, hopefully. But we wanted to know if the nitrogen cycle, which is strongly biologically modulated, is affected by this oxygen seasonality, and in fact, it is. So I will be explaining kind of the way in which nitrogen, or the nitrogen cycle, is affected by seasonality, and how we might be able to extrapolate that information to biosignatures and detectability on exoplanets. So hope to see you there.
Thank you, Emily. I'm not biased at all, but Emily's poster is fantastic and you should all go. There is also another really fantastic poster at our poster session about The habitability of high obliquity worlds and high eccentricity worlds too, and really intriguingly, the combination of really high obliquity and high eccentricity. My naive expectation was that that might be stressful for life, but life not only did okay, it actually thrived. And we were able to simulate more productive biospheres than present-day Earth under what I think are fairly extreme seasonal conditions. So I'm very excited about that poster as well. The lead author on that is Jonathan Jernigan over there in the audience. So please come to that poster too. All right, we have just about 10 minutes until our next scheduled talk. So how about everyone takes a moment to get some more water and chat with your friends about the favorite presentation.
minutes.
I know, I was planning on putting Emily on the spot if you didn't.
Okay. Posters. Yeah.
Yeah,
I
was
figured it'd
gonna,
be better if I did it.
yeah. I wasn't gonna do that to Jonathan, but Emily for
Okay.
sure.
Okay, Jonathan's not better.
I saw the look of panic on Jonathan's face when you suggested it, and he just was like, eyes got real big, and he's like staring at the floor. Yeah. All right, everyone, let's reconvene for our final very exciting talk. The last speaker of this session will be Austin Ware, who will be talking about pairing a GCM and Bayesian framework to predict habitable zone evolution.
Yeah. Hi, everyone. My name's Austin Ware. I'm a graduate student at Arizona State. Yeah, I'll talk about pairing a GCM Bayesian framework to predict habitable zone evolution. Try to make it under 12 minutes, maybe. All right. So first, let's talk about continuous habitable zones and define what that is. So continuous habitable zone, or what will be referred to here as a CHZ, is the orbital area remaining continuously within the habitable zone for some length of time. And so, yeah, obviously, as the star evolves on the right here, and the luminosity increases, the habitable zone will slowly move outwards. Right, but how long is long enough? So, like for a planet to reside within the habitable zone, because obviously we want to give that planet enough time to evolve life and have that life make a detectable impact on the atmosphere. And so for that, we look to Earth and the Great Oxidation Event as kind of a conservative estimate of how long. So it occurred approximately 2 billion years after the formation of Earth, which you can see on the right here, and obviously led to a very significant increase in oxygen in the atmosphere that would be detectable. And so we use that as a very conservative benchmark for how long a planet should reside within the habitable zone. But obviously you could look at other things like methane, which would have made a detectable impact a little bit before this. But yeah, so then we redefine the CHZ as the CHZ2, or the 2 gigayear continuous habitable zone. All right, and so we originally did this using models from Kaparapu et al. 2013 and 2014, which used a 1D cloud-free climate model to determine the habitable zone boundaries. See that on the plot on the right here. And so this is from the 2014 paper, and we use the three models from that for a 0.1 Earth mass planet, a 1 Earth mass planet, and a 5 Earth mass planet. But then there is also a 4th habitable zone that is not shown here,
and that would be the optimistic habitable zone, and that just assumes a recent Venus inner edge and a early Mars outer edge, assuming that they had liquid water on them at one time. And they would fall just further out of where you see Venus here for the inner edge, and a little bit further out of those outer habitable zone lines that you see there. All right. And so these models go into our Bayesian model to predict how the probability that a radius around a star has remained within the habitable zone for 2 billion years or longer. And so what goes into that? First, we have our prior probability that the orbital radius is within the CHC2. And so that combines Tycho stellar evolution models with the habitable zone models. And then that gets paired with our likelihood of the models given the measured stellar mass, metallicity, and age. And basically those two just get multiplied together to get our posterior likelihood, or the probability of the orbital radius being within the CHC2. Okay. And so our initial sample selection from my paper I published this year, we looked at Earth-like rocky planets, which we define as those having a radius less than 1.8 R-Earth and a mass less than 10 M-Earth. And we made sure they had installation values within the optimistic Kaparapu 2013 limits. And they were around host stars between 0.5 and 1.1 solar masses, which was that lower mass limit is defined by the Tycho catalog lower limit for the evolution models, but we've updated that to go lower now. And so we ended up with 9 potentially habitable planets, plus Venus, Earth, and Mars, and those 9 potentially habitable planets are on the right-hand side here. And so looking at the results from this initial analysis, we have the sun on the left-hand side here. And so on the y-axis is the probability that a given orbital radius is within the CHC2, and on the x-axis is the distance from the star. And so all of the black lines you see there are the different models from the Kaparapu papers. And then the colored bars are for the planetary radii. Orbital radii. And so we see that for all of the different models, it gives Venus a 0% chance of being within the CHC2. Earth is given a 100% chance for every model except the most conservative one, which is the 0.1 Earth mass model. And Mars is actually given a 100% chance for all 4 models. And you'll notice that is very much like a step function for the sun, and that's just because we have such a precise age measurement for the sun that we know really what radii are still in the habitable zone and which have left, et cetera. But then if we move to an exoplanet on the right-hand side here, another star on the right-hand side here, Kepler 442, we see that it's much more like a Gaussian distribution. Because ages for field stars are usually have errors on the order of about 1 billion years or more. All right, and so those are just the results from that initial analysis with the 1D climate model. But we wanted to use results from a general circulation model to compare to that. And so we used results from the Rocky 3D Land Planets Perturbed Parameter Ensemble. And I'm not going to go into great detail about what Rocky 3D is and how it works. But if you want to learn more about that, I would encourage you to go see Nancy Kiang's talk on Friday. But I'll talk a little bit about the Land Planets Ensemble. They used a Latin hypercube design. Again, you can learn more about that on Friday. But basically, they sampled 9 continuous variables, such as the stellar effective temperature, different orbital properties like solar day, obliquity, and also altered things like the CO2 content, the nitrogen content, a bunch of other things as well. Yeah, and so in the end, they ended up with 110 experiments, but after crashes and mistakes, there were about 84 final experiments, which still provided a robust sample of these different parameters. All right, and so the purpose of the Land Planets Ensemble, oh, I should mention land planets are not ocean worlds or things like Earth with oceans on them. It's a relatively dry planet with just some lakes and soil moisture. But yeah, so the point of that was, of their Land Planets Ensemble, was to look at the water inventories of these planets, and wasn't really to define habitable zone boundaries. So we had to come up with a way to define those boundaries for this data. And so what we ended up doing for the inner edge was doing a linear regression of the water lifetime for these planets. And so we did a linear regression on the observables of the effective temperature of the stars and the the relative irradiance of the planets, which is information that we can get from our stellar evolution models. And so we had to define a threshold for what to consider still habitable versus not. And so with water lifetime, obviously that's kind of undefined. How long does water need to last for something to remain habitable? So we just went with an extremely conservative estimate that lined up with our 2 gig-a-year continuous habitable zone, and just said that the threshold for water lifetime will be 2 billion years. But you could obviously change this and make this more or less conservative. Yeah. And so for the outer edge, we define that using the maximum mean surface temperature. So basically looking for an area on the planet akin to Death Valley that would still have an area that liquid water could exist on. And again, we did regression on the effective temperature and the relative irradiance, and made our threshold for surface temperature 0 degrees Celsius. All right, so getting on to the results from this, here again we have the sun, and the red solid line indicates just using the mean values from the regression, and then the dashed line is the 95% confidence interval. So because we don't input things like the CO2, obliquity, etc., we have errors on our coefficients from the regression. And so we can establish these confidence intervals here. Yeah, and so for the sun, we again project that Earth has a 100% chance of being in the continuous habitable zone, but actually Venus and Mars only have a 100% chance once you consider that 95% confidence interval. But then we can overlay the Kaparapu models onto here. It does get a little messy, but we can see that the mean values from the Rocky 3D model are shifted slightly inward and is a much tighter distribution than that from the Kaparapu models. But then when we factor in the 95% confidence interval, it becomes much more optimistic than the 1D model, especially when you consider the inner edge of the habitable zone. It goes much farther in. All right, and then looking at Kepler 442 here, the first thing you're going to notice is that that outer edge is completely unconstrained. And so the problem with using the data from this Land Planets Ensemble is that because they weren't looking to establish habitable zones, they also weren't looking to have their planets freeze over. And so there was an extreme lack of planets that reached extremely cold temperatures and ended up freezing over. And so that outer edge ended up unconstrained. But the inner edge is constrained. And if we overlay the Kaparapu models here, we'll again notice that the Rocky 3D model is shifted slightly inwards. And for the 95% confidence interval, it is again more optimistic than the 1D models. All right. But then, so what I'm going to do here is just kind of step through different stellar masses, starting with one of our smallest stars, and then getting to our largest star. And you'll notice that that outer edge begins completely unconstrained for this M1V star. But then as we go up in mass, it slowly starts to come down until it does become constrained with Kepler 452, which is about a solar mass star. Yeah, and so that just has to do with the regression. Once it becomes a high enough temperature and luminosity, it overpowers a negative value in our regression and becomes constrained there. But yeah, and then if we overlay the Kaparapu models again, we see that for all of these different models, the Rocky 3D values tend to be more optimistic, and the habitable zone tends to be shifted slightly inwards. Yeah. And so the reasoning for that we're still looking into, but it is the common trend we see. All right, and so just some conclusions here. Future ensembles should include a wider range of installation values, obviously, to account for this unconstrained outer habitable zone edge. The land planets ensemble habitable zone boundaries are generally more optimistic than the 1D model. And quantifying the uncertainty in the habitable zone boundaries allows us to establish these confidence intervals. And so I only showed the 95% one here, but you could decide how conservative you want to be and do, like, say, a 50% confidence interval or less. Yeah. And just the immediate next step will be to expand this sample to include all currently known potentially habitable planets, which we estimate to be about 30. All right. Thank you.
Thank you, Austin. Oh. Does anyone have questions? Yes, sorry.
This is on? Okay, cool. Hi, thank you for that talk. My name is Evan Davis, University of Washington. I noticed that you included early type M dwarf stars in your study, but late type M dwarf stars are quite different and can stellar activity goes on for much longer periods of time. So I was wondering, have you studied those yet in this work? And if not, what do you think that would do?
Yeah, so I showed a lot of some results from the previous work we did with just the Kaparapu models, and so at that time we only had stellar evolution models down to 0.5 solar masses, and so yeah, we just began with those larger stars. I have now expanded it down to 0.2 solar masses, and so we are going to get into doing smaller stars. Yeah.
Great, thank you.
Yep.
Any further questions? Yes.
Great, very interesting talk. What do you think is going on with the inner edge of the habitable zone, which, as you say, is well sampled in your grid and yet seems to be producing a distinctively different result than the 1D models? Is it something about moist greenhouse? I mean, do you know, I don't know, what is the physics that you think might be leading to that? So.
Yeah, so we are a little early in this, so I haven't determined yet if maybe it just has something to do with the fact that I've decided to use the water lifetime, and that might be, deciding where that line is, but yeah, I don't know the exact reason why it is shifted slightly inward right now, but that is something I will definitely get into as I start to write this up. Yeah.
All right, let's thank Austin and all of our speakers again. And this is your final reminder that if you like exoplanet habitability or exoplanet biosignatures, you should head downstairs to our poster session happening now.